So we'll get started. Okay, so this is the introduction to Coccinelle. So this is going to be a tutorial. So it's an interactive tutorial. I will talk for a while, and then you will do things, and then I will talk some more, and you will do things. If you have used Coccinelle before, or if you're extremely talented, you can just feel free to go on. You'll be able to download the slides if you don't have them already. You can go on to do the later exercises at any time. It's fine. So first I will introduce myself. So my name is Julia Lawal. I come from INRIA, and from Leipzig and from Evoulution. So I'll just introduce the ones at the beginning and end. INRIA is a research center in France, sponsored by the government. We do research on many different things. In my particular research group, we do research on infrastructure software. So the idea is, how can we better develop infrastructure software? How can we ensure that it's robust, and so on? So the Linux kernel falls very much into that area. And we have been working on Coccinelle now for almost 10 years, actually. And Coccinelle actually targets the Linux kernel, although it can be used for other C software. So I'm also affiliated with the Evoulution, and Roberto will talk about that more tomorrow. So the Evoulution is a research center on open source software in general. So in general, the word research comes up several times. So on the one hand, I'm here to present Coccinelle to you, present to you my work, to hope that you will use it in the future. That's why it's an interactive tutorial, so you can somehow get used to using it here. But on the other hand, I'm very interested to hear about what are your problems, and if you can see some kind of bridge. Coccinelle, maybe it's not exactly suitable for what you want. Maybe you can try to explain to me what your problems are, and maybe we can find something that we can work on together in the future. Okay. So just to get started, common programming problems. One problem is that programmers don't really understand how C works. Okay, probably everybody in this room is extremely expert C programmer, never makes any mistakes whatsoever, but maybe you deal with other people who contribute code to you who are perhaps not quite such good C programmers. So here's a very simple example. We have exclamation point, we have some rather random expression, we have an AND operation, and we have another random expression. So this is a problem that occurred in the kernel many times over the years. The idea is exclamation point is Boolean negation. It turns true into false and false into true. This is bit and programmers think we just want to negate the stuff that's coming afterwards. Here's the stuff that's coming afterwards. So it ands or doesn't and successfully, but that's not how C works. Actually, in C, this has higher priority. And so we take this expression, we get 0 or 1. Okay, so if you get 0, then this whole thing is just a complete waste of time, because 0 anded with anything is always going to be 0. If you get 1, okay, maybe it will do something, but it's actually probably not what you wanted to do. So this is a common problem. I think at this point it's mostly been fixed, but it kept occurring over and over again. Another issue that occurs often in the kernel is over time, the kernel API functions change. That is, the functions you're using inside the kernel perhaps when you make a device driver. So they change, new functions are introduced, new variants of functions are introduced, and you end up kind of with a mess. So some people use one function, some people use another function. Maybe it's not very clear why. Maybe it's not even consistent within a single file which kind of functions are being used. And it ends up with something that's very confusing. So other people who need to study the code in the future, they look at the code and they say, see, okay, we use this function here, but why? So it's very important for things to be used for a reason, to be using the modern version of something, and so on. And another common problem is that functions may fail. And often failures are not checked for, or they're not checked for in the proper way. And then sometime in the distant future, you'll have a rare error case, and then it will crash. So there's also lots of other kinds of very common changes that happen. What all of these introduce is a need for pervasive code changes. If you're using the wrong API, for example, you need to clean up that situation everywhere. If you're forgetting to check for error handling, for error cases, then you probably need to check for that everywhere as well. Okay, so here we have some examples. So this is a real bad bit end example. I've given you the actual file in which it occurs. This is all in Linux 3.2, so I had to go back a bit before we had cleaned up everything. So here you can see the code, but I mean, I've already told you what the problem is, so probably you can see the problem fairly quickly. But even just from this little tiny extract of code, there's lots of letters, there's lots of spaces, little black symbols, and so on. It doesn't really jump out to you that this problem is here. And then if you think about this in the context of 1,000 lines, in one of your 15,000 drivers, then you can see it's much harder to find the problem. One thing you could do is you could try to grep for an and sign and for an exclamation point. But in some cases, those things are on different lines, and so it's not particularly easy to find. Also, there may be other exclamation points and signs, the Boolean version of and those are all fine. So you may get many what we call false positives reports that are not actually problems. Here's another one, inconsistent API usage. So recently I've been studying Ethernet drivers, and I just look at the code and try to understand what's done and why is it done and so on. So I came across this issue. We have here PCI map single, PCI DMA mapping error in some drivers, and other drivers seem to use DMA map single, DMA mapping error. Okay, so these functions look kind of the same, with similar names. They seem to somehow have similar purposes. And so then you can ask yourself, why do we use one of these functions, one set of functions up here? Why do we use another set of functions down here? Okay, so maybe you could guess that, well, this one has PCA in front of the DMA, so maybe these functions are for PCI drivers. But then when we look down here, it looks like this must be a PCI driver as well. So then it's not really clear to me what's going on. So actually, these PCI functions are just wrappers for these functions down here. So you might want to decide that actually it's not worth the intellectual overhead of having these functions. We could just replace them all by this one. Or we could go the other way around and we could say to ourselves, whenever we have a PCI driver, then we want to use the PCI functions and change this case. So I don't have any particular opinion about which one should be done. Maybe somebody here knows which should be done, but that's not really the point. The point is that the code is not consistent and it's hard to understand. And the final example is the missing error check case. So here we have kmalloc. Kmalloc can fail because there's not enough memory. It's something that doesn't happen very often, but it could happen, and then the system gets into an inconsistent state. Here we have the kmalloc way up here. We have the first dereference down here. They're far apart from each other, so it's not so easy using for grep, for example, to find the cases where the test is missing. Often the test comes right after the call to kmalloc, but it's not always the case. Sometimes people initialize a bunch of things and then have the test, or perhaps the kmalloc is just going to be the return value. It doesn't seem necessary to test it locally. So for a bunch of different reasons, it's not easy to find these problems just searching in the normal way. So the goal that we have is to automatically find code that contains bugs or defects, or requires what we call collateral evolution. So the idea of a collateral evolution is you have an API function that changes in some way, so that's the evolution, and then all of the users of the API function have to be updated. So you have a function that takes a new argument, then you have to figure out what is the value of the new argument that should be used in all those cases. But basically we want to find complex patterns of code, and if it's possible to do so systematically, we'd like to fix those problems. So if you think about the exclamation point case and the ampersand case, we can just add a parenthesis and then we get the right priority. And we would like to make a system that's accessible to software developers. And so in our case, we have chosen to make a system that's very similar to the C code that you want to transform. Okay, so first we'll think a little bit about what we need in order to achieve these goals, and then we'll see how I decided to do that. So one thing we need to be able to do is to abstract over irrelevant information. So here is an example of our bit and situation, and basically there's some tokens in this sequence of little black squiggles that are important and some that are not. The if is important, the exclamation point is important, this is not important, this is important, this is not important, and so on. Okay, so some things, if we look at particular examples, some things in those examples are important, some things in the examples are not important for the particular problem we're interested in, and we want to be able to abstract over that. We also want to be able to match scattered code fragments. So we have the kmalloc case. We had our situation with the missing error handling code is we have a call to kmalloc, and then we have a dereference afterwards, and there's no test in between. So the kmalloc might be far away from the first dereference. So we need to match things that are separated from each other. And then we would like to be able to transform things automatically. It's nice to find where we have calls to PCI map single, but it's even nicer to be able to just transform them automatically and then check, of course, that the right thing has been done. Okay, so for this we have proposed Coccinelle. Coccinelle provides program matching, so you can search for things. Transformation, if you know what to do all the time, you can just do that automatically. And then it's for unpreprocessed C code. Okay, so the tool is going to be working on the code the way you see it. So macros are not going to be expanded, if defs are not going to disappear. And this is actually useful for a number of reasons. One is it's more efficient because we don't have to find all the header files and parse them. But also it has the advantage that you can reason about things like macros. Many macros, for example, might turn into 0. If you want to transform the macro to something else, you want to transform the macro itself. You don't want to transform all the occurrences of 0, which might relate to all kinds of different things. So the tool is based on a C-like patch-like notation. So the idea of transformation, patches, things, you remove some lines, you add some other lines. So that's the basic idea of the tool. But we generalized that. We called it semantic patches. So basically the idea is we take a little bit of the semantics of C into account in order to be able to generalize the ordinary patch. An ordinary patch just applies to one file, probably just to one version of the file. We want something more general that will apply to many files over time. So we have meta variables for abstracting over subterms. So we saw that in the if, exclamation point, and so on example. Some of those terms we're not interested in, so we're just going to represent them by meta variables. ... for abstracting over code sequences. So you have kmalloc. Basically, the idea of the kmalloc dereference example is that you have kmalloc here, and then somewhere afterwards you have a dereference. So it's natural to express that as kmalloc ... dereference. And we have a patch-like notation for expressing changes. If you want to remove some things, you put a minus in front of them. If you want to add some new things, then you put a plus in front of them. So here's our example. This is the exclamation point and example. And that's the problem. This is bad code. To solve the problem, all we want to do is just add parentheses around here. That's the thing that we're going to want to do in every case, regardless of what these two arguments are. So we want to do this automatically. And I'm going to say any random expression. Very commonly, it looks like what we have here, where we have some random expression on the left-hand side, and we have some constant, some mask that we want to find on the right-hand side. So this is the way that you can express this. So basically, this rule has two parts. The first part, here we have the @ sort of like a normal patch. In a normal patch, you have @ but you have line number information. Here we have what we call metavariable information. And then we have a pattern. So basically, our idea is if we have exclamation point, any random expression, and what I have here is any constant. So we consider a constant to be 3, or a string, or Actually, because we're targeting Linux code, which follows this convention, anything that's all in capital letters is a constant as well. So if you have exclamation point E and constant, then you want to turn it into exclamation point parenthesis E and constant. And so that's all there is, and then you can just apply this to the entire Linux kernel, and it will go around and find all the places that need to be fixed. So this is one rule. As I mentioned before, it has two parts, the meta variables and the transformations. And then if you need to do more complicated things, then you can make multiple rules. So meta variables, this slide is maybe more for reference in the future, but you can have meta variables which are expressions. So an expression is something that returns a value. 3 plus 4 is an expression, a function call is an expression, and so on. Statements. So statement is something bigger that doesn't return a value. So if is a statement, or a while is a statement, break is a statement, and so on. A type, so integer, Boolean, structure types, and so on. Constants, so constants are expressions, but they always have the same value, so 3 or something in capital letters. Local ID expression, so this is a bit obscure, but this is a variable which is declared in the current function. You can also have any type from the source program. So you can say this has to be an integer, or this has to be of a structure of a certain type. And then there's some other things, iterator, declarer, and so on. This is for like list for each in the Linux kernel. This is like macro, I don't know, different macros for declaring variables and so on. It's not very relevant for this tutorial. And then in the transformation, there are several options. One of them is you can put a minus in front of a line, and it will remove that line. A plus in front of the line, it will add something. If you don't know whether you want to remove or you want to add, but there is something that you want to search for, something important, you can put star. So these are two different worlds. This is searching, and this is transforming. And then spaces and new lines and so on are irrelevant. So you can put as much as or little as you want on a line, and it won't have any impact as how it looks in the C code. Okay, so now I have talked for a little while, so now it's your turn to do things. So I think Luis sent you enough harassing emails that you should have Coccinelle installed on your machine. So are there people who do or don't, or? Okay. If you don't have your machine, or if you don't have Coccinelle on your machine, you can also try to work with somebody nearby. So first I'll go over the exercise. This is just to basically type in the semantic patch that I've provided previously. This is saying how you can run it. And then you should always look at the answers and see if you're content with the answers or not. So by default, Coccinelle doesn't actually change your code. It just prints out a patch that describes how you can change your code. There's also an in-place option if you want to change your code directly. But in general, it's good to study your results and see if you're content with them before actually. It's not meant to remove completely the involvement of the human being. And then there's another exercise to try if you finish the first one. Then there's some practical issues here. If you do spatch parse cocci, and then the name of your semantic patch, then you can it's just like checking if the syntax is okay. It's probably a good idea. And there's some other options here, but they're not very relevant for the first exercise. In general, you may want to, spatch is going to print on standard output the result, a patch, and you might want to put it in a file so that you can apply it to your code later. It gives various output about what files it's treating at different times. You can use very quiet if you don't want to look at that. Yes, this is the source. Let's see what this is. I don't know what this is. I think you can ignore this completely. And this is the tutorial. It may be useful to download the tutorial to your machine so that you can look around on these different slides and see what you can do. So I'll go back here. Okay, so there's a question about whether C should be an expression rather than a constant. So there are, at least in, I mean, you can certainly try that if you prefer. But I have seen some old code, at least, that has this on both sides. And so then it is actually doing a bit and that's like a Boolean and, so it gives some false positives. So in general, the idea is that these specifications are supposed to be fairly easy to modify, and so you can try with something quite constrained first and deal with those problems, and then try to enlarge from there. So you can try it and see what happens if you get something different. Yeah. You got exactly the same answers? Okay. So that's an interesting question. That jumps all the way forward to the second hour, but I will explain it already. Sorry, which did you invert? You have C and not E. Okay. So sometimes there are different kinds of code that look a little bit different, but actually mean pretty much the same thing. So if you think about x equals null, null equals x, exclamation point x, if x is a pointer, it's all kind of the same. It's just different ways of writing the same thing. And an advantage of Coccinelle is it uses a C syntax. It's very close to what you see in the code. But then that's also a disadvantage as well, because it somehow can be overspecified. So this is a commutative operator. In general, whether you put this constant on the left or the constant on the right, it doesn't matter. And so Coccinelle has a thing which are called isomorphisms, which are collections of terms that are the same as each other. So if you write down x equals null, it will also match null equals x. And if you write down not E and C, it will also match C and not E. But actually, in the code that came out the other side, did you get expression and constant, even though you had constant and expression? Yeah. Either this one or that one, but it's always going to construct this one. So you can, I don't know if you think that's a good thing or not, but almost all the kernel code looks this way anyway, so it's probably better to make it more homogeneous. Are there any other questions? Okay, did everyone have a chance to finish at least the first exercise? Okay. Did anyone have a chance to start the second exercise? Okay. Yeah, I'll just move on. You can try it later if you have time. Okay, so our next example was the idea of inconsistent API usage. So here we have this function PCI map single, and one can ask ourselves if we really need this function at all. Basically, PCI map single just calls the other function that we saw before, which is DMA map single. And not very much happens over here. Here we're checking whether the argument is null before dereferencing it, but basically all we want to do is, instead of passing along the thing of this type, we want to pass along a field of that type. And the only other thing that changes is this cast here. Basically, there are a bunch of constants that are used for PCI map single, a bunch of constants that you use for DMA map single. Those constants have the same value, but one is in an enum type, so there's a typecast here to make the difference between them. But you can see that this function does so little that one could ask oneself, is it really worth the extra intellectual overhead to have this function? It's not just this function, there's a whole family of these functions. Do we really need to know about these two families of functions? So in this example, I'm going to assume that we don't need to know about them. We can just get rid of the PCI map single ones. So, for example, this code here would look nicer as this. Okay. What we save is we have one less set of functions. The cost is a little bit of extra code, but it's just a very little bit of extra code. It's not something that's going to make the kernel 10 times larger. Oh, so what we need to do is we need to change the function name. We need to add a field access to the first argument. And then there's something a bit subtle that's going on down here, which is, here we had PCI DMA from device. Here it has to become DMA from device. Here it's PCI DMA to device. Here it has to become DMA to device. So we need to rename the thing in the last argument. Yes? Okay, yes, I will repeat the question. So this thing that I have done here is a little bit unsafe, because now we are dereferencing. Yeah, I'm sort of answering the question at the same time. Now we're dereferencing something. We don't know whether it's null or not. But often in the context, one can tell already whether it's null. So I'm not going to address that issue in my rule, but you could make a more complicated rule, for example, to be sure that there was some previous dereference. If this expression has appeared previously, then you can safely make the change afterwards. Okay, but it's a good point. Maybe that's an issue that was taken into account. Okay, so that's another nice question. So the question is that actually this is the same number of letters, but here we've added some more letters, and so that's going to push what is over here off to the right. We're doing this using an automatic tool, and so if we make this change in 500 cases, then you might have to spend 500 tiresome hours afterwards to add new lines and move things around. Fortunately, Coccinelle is clever enough that when you change argument lists, it tries to deal with the 80-column problem by yourself. So I don't guarantee that it will give you the perfect answer in every case, but it will probably at least take this last argument here and put it down on the next line. So again, it's very directed toward Linux code and the conventions of Linux programmers, so we try to help with this. Any more questions? Okay, so we can get started. This is a commit that somebody sent at some point. And this person, to what my recollection of the commit message, this person thought that having these two different functions doing almost the same thing was pointless. We should just, for uniformity, just use the DMA version. This person did move the argument down here to the next line. However, one can notice that the person forgot to change the last argument. So now we have something even more consistent where we have the DMA function, but we have the PCI DMA arguments down here. This last argument I've personally found exceedingly confusing because the PCI version has no underscore here and the DMA version has an underscore here. So it's very easy to get something wrong. Here we see the different constants. You can see all the constants. They all have almost the same names, but not really. And they have the same values. And these are defined with hash define, and these are defined with a enum type. Okay, so to make a semantic patch for this, basically what we can do is we can take the patch that the person made, and we can generalize it. So some things are important, some things are not important. So one thing that's not important, actually we're only concerned with the function call. We're not concerned with what happens after it, so this we can just remove immediately. Now we can look around in the arguments, and there's some things that should change and some things that should not change. So this argument here doesn't change. It can be just some expression E1. This argument doesn't change. It can be some expression E2. And if we look more closely, we have another expression that doesn't change. Here we have adapter arrow pdev, and here we also have adapter arrow pdev. So this, it doesn't matter what that expression is, we just need to put the decoration around it. So we need 3 expression metavariables for these things that we don't care about. So we can add them in. Now I have expression E1, E2, E3. And this will make the change that the human made. Okay, but of course that's not sufficient because we need to change this as well. And so we can just do that. Okay, we don't like this one. We put a minus out in front of it, and then we put a plus with the thing that we do like. Yes, so your question is exactly what the next slide is. Actually, I've only done 1/4 of the work, because we have this constant here. This is the from device constant. We need to do the to device constant, the bidirectional constant, and the none constant. So we can make a bunch more of these rules. Just copy paste and change this thing down here. Okay, so maybe this is acceptable if there are 4 different constants. If there are 40 different constants, then it might be kind of tiresome. So we can try to do something a bit more concise. So here's another option. This time we only changed the part at the beginning. And then we have another part of the rule which changes all of these constants. So I don't know, are you smiling because you think it's a good idea or not a good idea? I don't know. It's kind of a trade-off. What was nice here is we could somehow see everything that was going on at once. What's not so nice here is we're kind of overwhelmed by this thing, and we've kind of not paying so much attention to that bit anymore. It's somehow not very understandable immediately. Because basically you have 2 parts. This happens always in the same way, and then we have all these things down here. So, but this is one way. It's fine to do it this way. So this is the idea of a disjunction. Basically, we have a bunch of different options. We have a vertical bar in between them, and we have parentheses. And a very important point is some things happen in column 0, and some things happen elsewhere. So from patches, you're used to minus and plus happening only in column 0. And it's the same for these parentheses and bars. They happen in column 0 as well. This parenthesis here is completely different from this one here. And it will complain if you put this one over here because it's not matching the right kind of parenthesis. Okay, so this is one approach. Another approach, though, is to separate out the problem into 2 different rules. In the first rule, we make the change on the function name and on the first argument, and we leave the last argument the way it is. And in the second rule, now we have the rules apply one after another. So in the second rule, we have already made the change we found in the first rule. And so now we want to match DMA map single. We don't care what the arguments are. They were just whatever. We've taken care of the first one. The others don't change. And then we can do this part down here. Yeah, okay, so the question is, why didn't I put a space here? Sorry, why didn't I put a space here? And it's because I was lazy and I made my system to accommodate lazy people. So if you like, you can, it's perhaps a good idea always to put a space in front of everything. If you do that, then you never have the problem with these parentheses appearing in the wrong place. But if you want to be lazy, you can also use column 0 for anything except parenthesis and bar and minus and plus. So, sorry, what? And star also, yes, star also. Okay, so this is another solution. So does anyone have any comments about the solution? Uh-huh. The idea of OR is you try this case, and if this case does not match, then you move on to the next case. Yes. In this particular example, it seems kind of trivial because these are all disjoint from each other. But in general, they might not all be disjoint from each other. And it always, you do the first one. If it doesn't match, you move the second one, and so on. Yes, so that's the issue, the difference between this one and the previous one. So the comment that Roberto made is that this rule does more than what we were doing before. What we were doing before, we were only addressing cases where we start out with PCI map single. And then we might adjust the first argument and we might adjust the last argument at the same time. Here we have two separate rules. This rule will apply. It will make DMA map single, but there might be other calls to DMA map single, and there might be other people who foolishly use DMA map single, but they use the PCI constants afterwards. And this will clean up that code as well. So then you can ask yourself, is this a good idea? Is it a bad idea? I don't know. It's up to you. Yes? Yes, so that's a good question as well. So that's why actually, if you look back at the example I had in the very beginning, this one, so our rule is not going to help with this one because in this case we have it buried in, these flags are buried inside some other expression. Mm-hmm. Okay. Okay. Just so I can repeat the question was, if we have a more complicated expression in the fourth argument with an or with an and, a bit and, or something like that, would it catch that? So from my point of view, it's the same as this one, but I can see perhaps it's not the same. In general, there might be a complex expression in the fourth argument and not just a constant. And the rule that we have here, actually both of the rules that I have, this rule and the next one, don't take care of that. They only take care of the case where this thing is here explicitly and nothing else. What you want in general, perhaps, is to take the fourth expression and look anywhere inside of it. And if any of these constants appear inside of it, then you might want to change them. And so there's another notation to do that, but unfortunately there's nothing to write on here. Okay, I'll try to do it in the error. You can have a thing like this, less than, greater than, and then inside of that you have a plus, and then dot, dot, dot. So the idea is a nest. It's like something, anything deeply in here can be changed as well. There probably are some other more obscure cases where they don't use this constant, where they use 0 or 1 or 2 or 3, and we're not going to catch those cases either. So you might want to, after you have done all of this, you might want to make another rule to find cases where we have PCI map single, but we do not have one of the, where we have DMA map single, but we do not have one of the approved constants. And then you might want to adjust those by hand. So it's possible to do that. I don't think I can explain it in the error like that, though. So, any more questions? Okay. So now we have an exercise. So basically, again, this exercise is just to try out what I have proposed. So you can implement any of the versions. Actually, you could try the third version and the fourth version and compare. So this is what we discussed, what Roberto answered the question for. And then you can also consider, actually, as I mentioned, there are about 10 of these PCI DMA related functions, and you would like to just change all of them. I think they all have the property that the first argument is this thing here. It needs the ampersand dev on it, and the last argument is one of these constants. So they're all kind of the same. So the idea is to deal with all of the kinds of functions and not have to make 45 different rules for that. Okay, so just I want to make the question was actually an interesting point. So what I have done in my rule here, for example, up here, I have PCI, the person was looking at this one, maybe. Here I have PCI map single E1, because E1 is going to change, but I don't have E2 and E3. I didn't put them up here on this line. What I could have done is I could have done PCI map single E1, E2, E3, and then DMA map single E1 arrow dev, E2, E3. If I had done that, then I would be removing E2 and E3 and adding them back again. So when you remove E2 and E3 have some nice formatting. Some human put some effort into deciding whether there should be a new line between E2 and E3, or maybe some new lines inside, and so on. When you remove E2 and E3 and you put it over here on the plus line, then Coccinelle is going to decide how to pretty print them. And Coccinelle works extremely hard to try to pretty print things in a nice way, but it doesn't always succeed. So in general, if there's something that's not going to change, it's better to just leave it the way it is. You'll get better formatting that way, instead of removing it first and adding it back. When you have your pluses and minuses and everything like that, you can put them freely anywhere you want. You don't have to put them on full lines of code. So here we have, for example, a minus PCI map single, open parenthesis E1 and comma. So that's not a meaningful unit of code, but it's completely fine. It's just removing these tokens and adding in these tokens. Okay, so the question is, can you have comments in your semantic patch? So yes, you can have comments in your semantic patch. You can just put them anywhere. They're comments for you. They're not going to match comments in the C code. We don't do any matching of comments in the C code. On the other hand, if you feel like you want to use Coccinelle to improve the documentation of your C code, you can use Coccinelle to add comments. I have never actually tried generating specific comments for specific places, but it might be possible to do. So you can add comments, you can put pluses in front of comments. If you have nothing in front of a comment, then it's just a comment for you. Yeah. Just use normal C comments. Okay, so has everyone had time to do the exercise? Okay. Okay, so we're going to have one more thing like this. This is something I haven't presented previously in the talk, but this is basically just the idea of getter and setter functions. So sometimes there are getter and setter functions in the kernel. Sometimes people don't remember to use them, and you have direct accesses to the fields. So when I first made some slides like this about 5 years ago or so, the example was platform get drive data or something like that, but then those have all been cleaned up, so I have to resort to this more obscure one. Okay, so our idea is just if we have any references to this field, then we should replace them by the call to the getter function. If we have any assignments like this, then we should replace it by call to the setter function. Okay, so that seems fairly straightforward based on what you've seen so far. So we have two rules. One is going to generate the getter function. One is going to generate the setter function. Okay, so any comments on it? Yeah. Yeah. Yeah, so the problem, the result is that this replaces any occurrence at all of some expression with arrow with data, and those expressions might appear on the left side of assignment, they might appear on the right side of the assignment, and so we're going to have these strange calls to IDE get with data on the left side of the assignment, and obviously that's not the thing we want. Basically what happens is the rule, as I said before, we have our file. Our file has many functions in it. We're going to take the first rule and apply them to each function one by one. And then we move on to the second rule, and we apply that to one by one to the result of the first one. So this rule here will never apply. So basically the solution is just to switch them around. So the point is just that you have to think a little bit about the order of the rules. Yes? Sorry, I've skipped past it. So the question, okay, so my solution to this problem is that we should just switch the order of the functions. Okay, so the question is there any other solution to this problem? So you might be concerned with another solution to the problem if you don't actually want to do the set case. You only want to adjust the getter case, and then you have to find some other way around it. And the other way that you can find around it is to use a disjunction. Okay, remember when with the disjunction, the parentheses and the bar and everything, I said it tries the first case. If that applies, then it does that. Otherwise, it moves on to the second case. And so what you could do here, you could put a parenthesis, and then you can put with arrow with data equals E. Just some random expression. And in that case, you don't want to do anything. And then you can put a bar, and then you can put this case down here, and then a close parenthesis, and then it will only update this one. So that's a way around it. Yes? So you, instead of having a single variable with here, you have okay, your source code might look like A, arrow B, arrow C, arrow D, arrow with data, right? Okay, that's absolutely no problem. I have said this is an expression. I haven't said that it's an identifier. I haven't said that it's called with. So this will match any expression at all. It can be extremely complicated. Is it clear? over here, if you have... Okay, so the question is if you have whiff data, arrow A, arrow B, arrow C. Is that the question? Okay, if you're doing an assignment like that, then you don't want to change that assignment, because this set whiff data is only for setting the whiff data field. Yes, you will. It will see that the thing is there. If you want to do it, then it does that already. If you don't want to do that, if you don't like seeing function calls on the left-hand side of an assignment, then you can again do something with OR to not match the cases that you don't like. Yeah. Yes, so this is a very good audience, because this is the second time you have asked me what's on the next slide. So, was there another question? Same question, okay. Extremely talented to the squared power. So here basically we were just assuming, I don't know, whiff data. There can't be very many fields named whiff data. So we don't really have to be more specific in that case. But there's many other fields that are a bit more ambiguous. Probe, for example. Many structures have a probe field. So I'm not sure what this is talking about here. Oh yeah, so we've already discussed this. We switch the rules and then everything is fine. It applies to 9 code sites, but now we're concerned about the types. And what you can do is, I mentioned this briefly at the beginning, you can write just expression for something, but you can also specify the type of the thing. And now it's only going to match ID with T. Okay, and so this one raises a particularly interesting issue because ID with T is probably a type def. And there might be another level of inconsistency where some people use the type def and some people don't. And so if you use the type def in your rule, it's actually only going to know about the type def. But if you go and find what the type def points to, because actually in the kernel you're not supposed to be using type defs anyway. So maybe this is struct ID with. If you put struct ID with here, star with, then it will, if it knows about the type def, it will understand the relationship between the two things. And so it will update both the case with the struct blah, 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 and the case with the type def. Okay, so there's a trade-off in here. If you just put expression, then things are not very safe because it might be getting things of the wrong type. If you put ID with T here, then you will be safer because it will only match things that it knows have type ID with T. Okay, but the key point in that my sentence there was things that it knows have type ID with T. There might be things it doesn't know the type of. And if it doesn't know the type of something, it's not going to have this type, it's not going to get matched. So what happens is, by default, well, the default string is a bit strange, but Coccinelle has different levels of inclusion of header files. If the type is locally in the function, everything is fine, always. If the type is in a header file, maybe this with is not just a local variable, maybe it's A arrow B. You have to find the type of A and then find the type of the B field. So to do that, you find the type of A, that's going to be some structure. You have to find the definition of the structure. The definition of the structure might be in a header file. It might not be obvious to Coccinelle where that header file is. So in general, the most efficient thing to do, Coccinelle is perfectly happy to just take the C files with no header files at all, and then it will cope with what it can for the macros, and it will not have very much type information. If you know you need more type information, then you can include like header files that have the same name as the file. So often there is like foo.c, and that goes with foo.h. Or you can include all of the header files which are included in the current file. Or you can include header files which are included by other header files. Or there's a more complex option where it just searches over the entire Linux kernel to find a header file that has the name which is mentioned. The problem is, one thing, we don't want to interpret make files. And the other thing is we don't want to spend hours to parse 25,000 lines of header file for each C file. So in general, having the least information possible is going to be the fastest. And then you have to decide how much more you need to do your work safely. Yeah. Yeah, so there's a question about adding this header file search path to the command line. You can indeed specify as many search paths as you want. And if you know where your files are likely to be, then that's a completely fine solution. If you want to, if you have decided to introduce the function IDE set with data into the kernel and you want to update all of the uses of these fields, then maybe you don't know where everybody's header files are. And so then in that case, you might not have perfect information. But if you know your code, then that's certainly an adequate solution. I think there was another question. Yes. Okay. So the question is, often one is working on a subdirectory of one's own code of interest, and you only want to apply Coccinelle to that directory, but when you get patches, you want actually your patches relative to the root of the kernel. And so there is a option which is -patch, -patch, and then you put the prefix of the path that you want. So mine might be home Julia Linux. So I might be working on home Julia Linux, drivers net Ethernet. So that's the thing I would give for the dir option. And then for the patch option, I would give home Julia Linux. Yeah. Any more questions? Yes. Which one? Okay, yes, of course, yes. Yes, so that's a problem too, that, yes, they will both match the definition, and so what you can do is you can make some more rules beforehand to ensure that that doesn't happen. In general, I don't know, it's a bit more complicated. One solution, the extremely cheap solution, is just to live with it, and then you can take the patch that you get out and you can remove the bits you don't want. Okay, then you don't have to learn anything new. The other solution is that you can match certain things in one rule, and then you can record the position of those things that you matched, and then you can say that the things that you match here should be at positions that are different than the ones that you matched before. So it is sort of like the concept that I mentioned before with the disjunction, where you have some case in the disjunction that you don't want to transform, and then other cases that you do want to transform, but it's in between different rules. So it will find that in the file abc.c on line 27, there's a call to with or with data, a reference that you don't want to transform, and then you can specify here that you shouldn't transform it. So at the end of the talk, you'll see how to put in positions. It's a bit hard to explain at the moment, though. Any more questions? Okay. Okay, so I'm going to just skip exercise 4. Exercise 5, you can look at them on your own. Basically, we've seen so far is meta variables for abstracting over terms. meta variables that are restricted to particular types. We saw disjunctions, we saw the multiple rules, and the importance of ordering the rules in the right way, sometimes anyway. Okay, so now I'm going to go on to part 2. So if you downloaded the slides, you have them just concatenated with each other, but I have 2 separate files, so. Okay. So this is advanced features. So at the end of this, then you'll know how to do almost everything with Coccinelle. Maybe not quite everything, but. So isomorphisms, this is something that came up already. So we'll see it in a little bit more detail. Dots. So this is what I mentioned briefly before, ... If you have kmalloc and then you have the dereference, you don't know how far afterwards the dereference comes. And then positions, which I mentioned just now. And we can also interface with Python and with OCaml. And so then you can mix matching against code against doing other kinds of computation. So isomorphisms, I talked about this a little bit already. Coccinelle matches code exactly as it appears. Sometimes that's what you want. Sometimes it's not quite what you want. Sometimes it's overspecified. And the problem is if you write x == null, then it's not going to match exclamation point x. And so then you'd have to have a bunch of disjunctions in your code to match all the different possibilities. And then it gets to be, there's a lot of these things you might not think about them in advance, but your patterns would get very complicated. So what we want to do is transparently treat similar code patterns in a similar way. So here's a macro div roundup. This is a use that someplace where we ought to be using this macro. This macro div roundup, maybe the English words are sort of intuitive. This computation here is not at all obvious. It's got a bunch of operators. It's got a bunch of parentheses and commas and so on. So the macro is defined this way. What we would like to do is use the macro in other places where it could be used. And so we want to make a semantic patch to, it's sort of like the getter and setter option. We want to transform cases that look like this into cases that look like this. But again, if we look up here, this case up here doesn't look exactly like this. Down here, there's all these parentheses. The person was being defensive in writing their macro, which is certainly fine, but normally people aren't that defensive when they write their code. So then we have a problem. How many parentheses should we put in our semantic patch? So one solution, we could make this something fully parenthesized for the very defensive people, and we could put something completely unparenthesized for the less defensive people. So we could give 2 options. That's probably the limit of what humans have the patience to do. But there's lots of permutations that are available. There's a bunch of parentheses there. They could all be present or not present. And so we have the idea of isomorphisms. Isomorphisms are user configurable. There's a file called standard.iso. You can write your own isomorphisms if you think of some other things you want to do. This is just 3 commonly useful ones. This is, so we can start with this one in the middle. This is the one that's going to be useful for div roundup. If we put a parentheses in the specification, then it will pretend that the parentheses are not there as well. It will match either the case with the parentheses or the case without the parentheses. This arrow here means that if your semantic patch has something that looks like this, then it will also match something that looks like this. The arrow doesn't go the other way around here. The arrow goes the other way around. So what this means here is it's not going to spontaneously put parentheses everywhere. That would be probably way too expensive. You have a responsibility to figure out where parentheses might be possible. Then you can put them in, and then it will consider also the case where they're not there. Similarly for casts, there are some places in the kernel, especially in older code, where you had like kmalloc or something like that that was returning a void pointer, and then people would cast it explicitly to some other more descriptive type that they would then store the result in there. But those kinds of, and so you have some code that has the cast and some code that doesn't have the cast. So if you think the cast is important, then you can put the cast in there. And then it will consider either that the cast is there or it's not there. I'll answer in just one second. So this important thing about this this cast here. You see this meta variable here, it's representing a type, but I have put pure type in front of it. And what that means is that it can only match a meta variable in the semantic patch, and that meta variable can't be used anywhere else for any other purpose. So it's not something constraining a match, it's just a type that's just holding a position. So if you have a semantic patch that says, in parentheses, int x, that will only match int x. It won't match x. If you have a semantic patch which has type t, and then has t in front of kmalloc, then it will also match kmalloc that doesn't have the type. So, sorry, what was the question? Yeah, okay. So each of these isomorphisms has a name. One is called drop cast, one is called paren. And the idea is sometimes maybe you really want to match parentheses. And so you can disable the isomorphism. Or if you really want to match cast, then you can disable the drop cast. And then the last isomorphism I have here is just with the nulls. If you have x equals null and null equals x, or exclamation point x, it will interchange them. So basically, we're going to write just this in our semantic patch, and then Coccinelle will take care of all the other permutations. So internally, your semantic patch can be absolutely enormous. There are a few times I have run into the case where actually the semantic patch got so big that just parsing the semantic patch was the bottleneck and not actually running the semantic patch on the code. But in general, it works out okay. Yeah, so we have this, and so now this specification will change to 181 occurrences in Linux 3.2. Yeah, so there's some things you can do. Here's the disable that was already asked about. You can also add your own isomorphisms. So you can say put them in a file using the same format, and then you can say using that file. So if you don't care, for example, about the difference between spin lock and spin lock IRQ save and so on, then you could make an isomorphism for that. And then your semantic patch would be simpler. I haven't found this in practice. I haven't found this feature to be terribly useful. This is fairly useful. Another thing that's useful is if you want to just get rid of all isomorphisms, then you can make a file called empty.iso, and then you can use that as your isomorphism file, and then your semantic patch will do exactly what it looks like it does. So we don't have that much time left, so I think I'm just going to move on and skip the exercise. But the idea is, we didn't see it before. I didn't put this on here. Another thing that's very useful to do if your semantic patch does not seem quite to be doing the right things is to see what its interaction with isomorphisms is. You can do spatch parse cocci and then mysp.cocci, the name of your semantic patch, and then it will show you the semantic patch with the isomorphisms applied. And it can also give you some error messages if it looks like your isomorphisms should sort of apply. It will try to explain to you why it didn't. So that can be useful sometimes also. Okay, so probably the most important thing left is dots. So sometimes all of the rules that we have seen so far are completely atomic. You just look for some expression, some function call, some dereference, and so on, and then you make some change to it. In general, you may want to find things in different places, and then if all of those things are present, then you want to do something. So what we want to be able to do is to specify patterns consisting of fragments of code that are separated by arbitrary execution paths. So this is important when you say we have A here and we have B here. Often you want there to be some actual connection between them. We mean that when we write A ... B, we mean that first you execute A, and then after a while you will perhaps have a means of executing B. So it's not just two random things at random places in the code. There should be some connection between them. And then also often it's useful to be able to specify some constraints on what happens in between them. And so we'll see examples about that later. So here's our example that we had at the very beginning. We have kmalloc. Kmalloc returns some value. That value might be null if the allocation failed, or it might be the thing we're interested in. If it's null, then you ought to check for that and abort or do whatever is appropriate. So this code here is fine. Here's some code which is not so fine. This person just says G equals kmalloc, and then there's just a dereference immediately afterwards, and if it fails, then this will crash. Okay, so this particular case would be easy to find with respect to what we've done so far. We can say expression equals kmalloc, and then the different arguments. Expression arrow field, some identifier, and then equals whatever, so something like that, and that would be a problem because you have the kmalloc and the dereference right afterwards. But we saw the example before. The kmalloc is here, and the dereference is 5 lines later. So in general, the problem, it can't be solved just by looking at the next line. You need to see the connection between things. Okay, so again, if we want to make a semantic patch for this, we use the methodology we had before. We take an example, and then we generalize the example to make appropriate semantic patch. So here's our example. The important things are the call to kmalloc, actually the name of the return expression, and the dereference down here. And this stuff in between is just whatever it is. We don't care. But the important thing is that when we start here, we will eventually end up executing the code that's down here. Okay, the first thing is, I understand that this is a problem, but I don't know how to fix the problem in general. In general, I'm going to need to write some error handling code. What that code is depends on the things that have been done before. And so I don't have some general solution, so what I'm just going to do is put star here, and then it will inform me about this problem, and then I can think about in each case what I should do. So we have the star. Now we can get rid of the stuff we don't care about. All that stuff in between is just going to be ... And then we can simplify some more. Alloc, I said that's important because we want that the return value of kmalloc and the dereference thing are the same. But this context in which the dereference occurs doesn't make any difference. So we can get rid of the context, and we can add an expression meta variable for the result of kmalloc and an identifier meta variable for the field that we're doing the dereference for. Okay, any comments? How do you match the variable that gets passed to? Okay, so here I have the question is what happens if this E is passed to another function? How would I match that? Here I have an explicit dereference, but you're concerned that the dereference might not happen here. It might happen in some other called function. If you are suspicious of all other called functions, what you can do is, so here you see I have ... for the list of arguments. We can do ... for a sequence of statements. We can also do ... for a sequence of arguments. So basically your problem is you have some function, let's call it G, because I've already used up F. We have some function G, and somewhere in its argument list, E appears. So then you can say ... comma, E, comma, ... And that will match wherever it appears. Then there's also the more complicated question. There's some functions that dereference their arguments and other functions that don't dereference their arguments. And so then now we don't know whether all the G's are important or not. And so there's not an easy solution to that. Coccinelle is intra-procedural. It only looks within one function definition. Yeah. Okay, so yes, so that's the third point we'll see on the next slide. So we have again, okay, yes, so that's the issue. This rule here actually that I've written is completely silly. It's going to match any call to kmalloc at all with any dereference of the allocated thing. Okay, so it will match basically probably every call to kmalloc in the kernel. That's certainly not what we want. I put dot 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 here because I didn't care about the stuff that was in between, that was explicitly in between, but I do care about what happens in between. One thing I care about is I care about that there's no null test, because if there's a null test, then everything is fine. Another thing I care about is how do we know that this E up here is still the same as the E down here? Somebody could reassign E in between, and then the k-malloc is irrelevant. Okay, so we can address both of those issues by putting some decoration on the dot 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 here. So the first one here is when is not equal to E equals null. When is not E is not equal to E not equal to null. So basically what I'm assuming here is if there is a null test on E that comes before the dereference, then the programmer has thought about this problem and everything is okay. Okay, that might be a wrong assumption. He might have thought about the problem but not in a sufficient way, and one could study those cases later in a more complicated way. But for now I assume that if there's a test, everything is good. And then I can also say when there's not an assignment of E to something else. So basically here we are at some place in the code we have a k-malloc, and here we have a dereference, and then we look at all the code in between, and there's no update and there's no null test. Okay? There's another, yeah. Okay, so your example, we're assigning E each time. So the question is E equals k-malloc, check for null. E equals k-malloc again, the same E, and then dereference with nothing, okay? So basically, mm-hmm. Mm-hmm. And then the assignment or the test then, going to the first location. Okay, so there are two cases one could be concerned about. One of them is where we define E 2 times. So I'll answer that one first, and then I'll answer the second case, which is where we have 2 different assignments for k-malloc. So in the first case, this pattern here, it can match at many places in the function. Basically, it's going to start trying to match every place where we have E equals k-malloc. And so we will come to our first one. We will see the null test, and we will give up on that one. But then we will come to the second one, and it will not have E equals null. And then we will give an error for that one. So that case doesn't pose any problem. So then there's another question is, here we have E equals k-malloc, and then maybe we have X equals k-malloc, and maybe we have a test on E, and then we have a dereference to X. So I think that situation is actually exactly the same, because we will have one match that starts out at the E equals k-malloc, and another match that starts out at the X equals k-malloc, and the E equals k-malloc one will only be looking for tests on E, and the X equals k-malloc one will only be looking for tests on X. So these things can overlap each other in any random way. Yes, yeah. It takes your entire function and tries every place that you can match inside the function. There is another way you can ask the question. So you've asked the questions about the beginning part of the match. There's also questions about the end of the match. So there may also be many dereferences of E. And it's not clear that you really want 500 reports if there are 500 dereferences. You probably only want the first report. And so that's what happens. Actually, implicitly ... says when there is no occurrence of this inside and when there's no occurrence of this inside. So it gives the shortest match. Yes? Mm-hmm. Okay, so First off, I really hate when people do that. Okay. I don't think that was the answer you were looking for. Okay. So the second answer is, okay, so this rule, this is actually a kind of subtle point. This rule here, this line here, I have expression E equals k malloc arguments. So if you think about the grammar of C, it's a little bit obscure point, but an assignment is not a statement, it's an expression. So here is an expression, and then I've put a semicolon on it, and I have turned it into a statement. And when I put the semicolon on it and I put the statement here, that means that it is only going to exactly match this statement. So your case would not be matched at all. If I had been more clever and I had left off the semicolon, and in general, when I write these rules, personally, I leave off the semicolon, so I'm not sure why I put it there. If I had put it without the semicolon, then this will match this expression wherever it occurs. And so in your A equals B equals k malloc case, it would be able to match at least the B equals k malloc. But it's not going to help you with A. So I have no solution for A. Yes, sure, that happens too. If you are concerned about that, then you can, I mean, in that case, or actually in both of the cases, you have to deal with it yourself. You have to write the more general rule, which case is the case of A equals B equals C, and the more general rule of, here you could have X equals E, and here you could have either E or X, and in your whens, you could do either E or X. And so this double assignment thing is very unpleasant from my point of view, because then there are two cases that do the same thing and the syntax is completely different and there's no way to do anything in general. So any more questions? So let me just, okay. So this rule was very nice. It finds some bugs, which is nice. Here's the one that we saw before. But it also finds some false positives, which is not so nice. Okay, so we can think about what happened here. Here we have our k malloc. It's going into irec arrow opt. Here we have irec arrow opt is not equal to null, so we have a test. And here after that we have a, it looks like a dereference. Ultimately it's going to be a dereference of that thing. But everything over here is safe because we had the null test over here. But unfortunately, Coccinelle only knows about the order of evaluation between statements. It doesn't know about the order of evaluation from the left side of an AND to the right side of the AND. So actually, if we go back to our rule here, what it says is we have our k malloc, that's one statement. We have this, which is another statement. And we're checking all of these statements in between. And actually, in our example here, there are no statements in between. And so it's obviously going to be satisfied because those things that we were supposed to find are not there because nothing is there. So actually, that particular strategy is not going to work terribly well. We can take another strategy, which is to start at our k malloc and look forwards. And when you look forwards, then there's three possibilities. You might come to a E equals null. If you come to E equals null, then everything's fine, you're done. If you come to E is not equal to null, everything's fine, you're done. That is, we don't want to report any match, the code is perfectly okay. And if when you look forward, you find a dereference of E, then there's a problem, and then we want to report that one as a match. So we can reorganize the rule like this. Here we have E equals k malloc, here I have dot dot dot. I have when, I keep this when, which is for reassigning E. And then I have three possibilities. We might come to a null test, or we might come to a non-null test, or we might come to a dereference. In my null test and my non-null test, I have put or whatever, and whatever, and there is a isomorphism that will pretend that they're not there if they're not there. Yes? If, so you want to put the, you have the assignment inside the if condition? Yeah. It's not a bug, and it will be highlighted to the user. I mean, it's another false positive. Or nothing will happen, actually. Let me think. You have, do you have a null test or not in your example? So you have the assignment and e equals null. All on the same if. So have you ever seen code that looked like that? Actually, I've never seen it, so.
People that see it poke themselves in the eyes.
That's a good point. But yeah, no, I've never seen it, and it would not, it's not going to detect it. First, I have this stupid semicolon here, so it's not going to work for assignments inside of tests. If I remove the semicolon, then it's still going to be the case that it's just going to match, it's going to focus on the kmalloc part and start checking after the if header. It won't be checking the later part of the if header. So it will probably give you a false positive, and then you will see the code and you will, as was suggested, before poking your eyes out, you might want to reorganize the code a bit, and then things will be better. Yeah. No? This one? Here's the false positive. Here's our good example. Okay, so the question is, we have this code like it is. We have this code like it is also. And down here, we also have a dereference to irec opt, right? But the check has, oh yes, because of its and. So it's not also not going to realize that that's safe. It's going to be a false negative. It will think it's safe, but it's not. I think that is why, yeah, I'm not sure I can think clearly about the question at the moment. But notice here I do have this and. I wonder if that's somehow related, but I'm not sure. Any more questions? Okay, so this is the semantic patch that we end up with. So do you notice anything objectionable about the semantic patch? I don't know, you've noticed a number of objectionable things, but there's one objectionable thing that has not been discussed. When I started out with my semantic patch, I had a star up here and I had a star down here. That was very nice because the dereference could be 20 lines later. And then if there's no star up here, then you're going to see a report which is going to inform you about the E arrow F, and then you'll have to hunt backwards to find out where the kmalloc was. And actually, the way the star works is it makes like a diff, and it puts a minus on the lines which are starred. So there might be many dereferences on that line, and you don't know which one. And the reason why I had to remove the star up here is because the star is going to happen whenever there is a match. And now I have a match in this case, I have a match in this case, and I have a match in this case. And so I would end up putting stars in front of every kmalloc. So basically we want to be informed when this thing appears and when this thing appears, both of them. We don't want to be informed when this one match happens and when this match happens. So we'll skip over the exercises. There's lots of interesting exercises here, but I'll go on. So we have positions to help us with that. So I mentioned positions briefly before. This is what I just talked about. I mentioned positions briefly before. There's a way to find out the position of anything that you have matched. So we have meta variables which are called position, P1 and P2. Now I put the position variables on the things that are interesting. So I've attached P1 to kmalloc, and I have attached P2 to E. And then I can make a rule in Python. And Python is we're going to inherit those position variables that we matched back here. This Python rule will only happen if all of the inherited variables are matching, and then it will print out a helpful error message that will include both positions, and then you'll be informed about this line and this line. Okay, so this is a little bit fast. There's a bunch of new issues here. One of them is that we can use Python. You can also use OCaml. Another issue is that you can give rules names. So we saw already that the isomorphisms could have names, and we could disable them, or then we could disable them. But we can also, ordinary rules can have names, and then we can make one rule which is going to inherit the meta variables of another rule. So this rule here, it might match in 25 places. So we'll get 25 different sets of positions. And then this rule will be applied 25 times for those different positions. In the Python code, the positions that you get, the information, each position is an array of positions. And you get a line number, you get the file name, you get the column number. This is the starting line, ending line, column, starting column, ending column, file name, and the name of the enclosing function. So you get a bunch of information. I think that's all the new things here. Any questions? You can also, something that's interesting to do, which goes back to what was asked before about we don't want to change the definition of the get with and set with. You can also, these positions can be anything, but a position can be different from some other position. So you can find a position, you can find a call to kmalloc that has certain properties. And then in another rule, you can make another position variable that has to be different than the positions that were matched here. So that gives you a lot of control over the relationships between things. Okay, so then there's another fairly complicated issue is ... So what does ... really mean? So one issue that we've talked about ... is the things that it can be matched in between the thing before and the thing after. And that ... is the shortest path between the before and after things. So another issue that's not so obvious about ... is in general, you start at some place in the code, and then you might have just straight line code afterwards, so then there's only one path that's possible. Or you might have an if that comes afterwards, and then there might be several paths that are possible. It might branch out. And when we are doing transformation, well, basically, when we're doing star, it will search for the existence of one path. When we're not doing star, it requires that all of the paths match. And so that's not necessarily what we want here. If here we want to search for a bug, so we just want to say, does there exist a path that has this property? So it's kind of a subtle issue. Okay, so I have, yeah, there's a bunch of fairly interesting exercises here, but we'll skip over them because we're pretty much out of time. Overall, we've seen isomorphisms. Isomorphisms let you write things in one way and let them match things that look a little bit different. We've seen dots for matching sequences. You can match a sequence of statements. You can match a sequence of arguments as well. In general, anytime you might not really care about what's in a certain place, if you think intuitively you'd like to put ... there instead of putting something, then you can put ... On the other hand, we had when, because often when you have ... you actually want to put some, you do care a bit about what's in there. You want to put some constraints on it. You want to say certain things should not be matched in that region. And then we have positions for remembering the positions of code, Python for doing other things. for printing. It's very useful for printing error messages in some particular format that you find useful. Also, if you want to collect information, you might want to put it in a hash table. If you want to know what are all of the possible first arguments to the function f, you can match the function f. You can get its first argument, you put that in expression, then you inherit that into a Python rule, and then you have a string, which is the first argument to the function f, and then you can store that in a list or hash table, whatever's appropriate. You can also, it's also good for doing metrics. How many times do I call spinlock IRQ save? You can make initialize a variable at the beginning of the semantic patch and then print out the value in the end and add one each time you come to spinlock IRQ save. So that's all. Are there more questions? Yes. Okay, so I'm not completely sure to understand the question.
So there's a function pointer, let's say 2 arguments.
Mm-hmm.
Now I want to transform this into 4 arguments.
Mm-hmm.
So having a function pointer definition is easy, but all the instantiation of that function is would have different names.
Okay. Okay, first I will answer your first question about regular expressions. Yes, you can use regular expressions. Personally, I don't think regular expressions are a good idea because not everybody uses the word get meaning the same thing, for example. And so it might end up matching things that are undesired. But you can say identifier equals tilde, and then you can put a regular expression afterwards, and then it will match, that identifier will match all things that have matched that regular expression. Okay, so then the second question is, how do you deal with function pointers? Maybe your function pointer is in a structure, and you have a certain type, and then there's a field. So to be concrete, platform driver probe function. You want to update all of the platform driver probe functions to take an extra argument. So what the nicer way to do, so you could search for, maybe everybody has thoughtfully named their probe function probe, something probe. So you could change them all. That would probably not be very successful because there are other kinds of probe functions. So it's not very safe. And some people don't name their function probe. So what you can do is find all of the places where you have defined, where you have a structure of type platform driver, arrow probe equals f. So now you have the name of the function. So you have one rule which will find the name of the function, and then you make another rule which is going to inherit the name of the function and find the definition of the function. And then in the second rule, then you can make the extra parameter or do whatever you need to do. So this works best when the function pointer is initialized in the same file where the definition of the function exists. Yeah. Yes. Sorry, I didn't hear the last sentence. Mm-hmm. Mm-hmm. Okay, so I think you asked two questions. One is about parsing, and one is about some things seem to be hard to check for. So I'll answer the parsing one first. So we try to parse everything. Sometimes in a file, there's some things you can't parse, and so we try to recover and go on. Sometimes if there are macros that have some strange arguments, like sometimes a macro will have plus as an argument, which is not an expression, it's not anything. Sometimes we'll skip over just the arguments of that macro and still be able to parse the complete function. So then the second question is, the rules that I have written, sometimes there are strange ways that the code can be structured, and then the rules is not going to match. And in general, you need to refine, if you find that to be a problem in your case, you need to refine the rule to distinguish between the cases that you want to find and the cases that you don't want to find. It may be, so in a case, for example, where you are planning to change the name of some function under certain conditions, then you could have the rule that that does the transformation in the right way, and then afterwards you could have another rule that matches the remaining calls to that function and prints out some message. You had better look at this definition of this function on line 37 of file foo.c, and so then at least it can inform you that some things were not taken into account. Other questions? Okay, thank you.